Hello, this is Mr. McGovern, and this is the fourth video in the AC electricity series, and we're looking at transmission lines. So we're going to be looking at these ways to transfer electricity from our power plants to our houses, and specifically why do we step that up to such a high voltage to transmit. So we've got this diagram here. You can see the power plant gives off 12 kilovolts. That's what it generates at, but we use a transformer, which we looked at in the last video, and we step that up to a much higher voltage, 400 kilovolts, to transmit it towards the cities, and then in the city we step it down with at a substation and step it down again for a house. So why don't we just generate it at 240 volts and transmit it the whole way at 240 volts? Why do we have to have all of these things in between? So we saw last video that there is a formula that can calculate how much we'd step up and step down the voltage, and that depends on the ratio of the number of turns in the primary and the secondary coils of the transformer. So in this case we have we're starting from 12 kilovolts, and I'm just looking at the right hand side here. So the voltages dividing one by the other, 12 kilovolts over up to 400, and that ratio when drilled on my calculator is 1 over 33.3. So we step up by 33.3 times. So that means they've got a transformer in there where there's 33.3 times more coils in the secondary than the primary. So why do they do that? What's important about that? So the reason is that transmission lines, they're not superconductors. They're not absolutely perfect. They have small resistance, and that resistance on paper looks very small, say 0.1 ohms per kilometre. The issue is say for example in New Zealand, a huge fraction of electricity is generated in the lower South Island. Okay, at some mountain lakes, Lake Pukaki and Tekapo. But then we need that electricity in the cities. We need it in Christchurch up to Wellington, into the North Island. Now that's hundreds, thousands of kilometres it has to travel. And so when you have that small resistance per kilometre, it adds up over many, many kilometres and it becomes an issue. So why do we step up? So the reason is that in our transformer, the power in is the power out, right? And we know power is voltage times current. So if the voltage steps up, in this case by 33.3, this is the really important part, the current steps down by 33.3 times. Why is that important? If we were to look at within the transmission line, getting the hundreds or thousands of kilometres to our house, and we treat this as sort of a resistor in series, if we were working out how much power we're losing in this resistor, we'd always do it times V times I, and we don't know what that voltage loss is. We can work it out though with I times R, and what we can do is we can substitute this into the other formula, and so we get P lost as I squared R. That comes from the fact that there's an I in this formula, and I substituted in this V loss because I don't know what the voltage lost is, and so there's the second I in here in the R. So the loss power is given by I squared R. Now, when we increase the voltage in our lines by 33 times, remember we decrease the current by 33 times, and now because power is proportional current squared, in this case we decrease our power lost by 33 squared times, which is like over 1,000 times. So this stepping up has a huge effect on the power lost throughout the transmission lines. So as an example question, this is from 2023, it says that Kate's area generates 50 kilowatts of power. There's a transmission line that takes it at 220 kilovolts, and the resistance is 4 ohms for every kilometre, goes to 300 kilometres. So calculate the power lost. So what I'm going to do first is, remember, I want the current. The current's the key. We want to minimize that as much as possible, and that's how we work out our power loss. So I've been given the power output of the transformer, 50 kilowatts, and the 220 kilovolts. I do power divided by voltage will give my current, 0.227 amps. And now I'm going to use this P equals I squared R. So in this case, the 0.227 amps squared, and my R is 4 ohms per kilometre, but 300 kilometres worth. Multiply that together and I lose about 62 watts. So not much, because I've got such a high voltage and such a low current. However, it says in the second part of the question, comment on whether this amount is significant compared to when it's not stepped up but transmitted at 25 kilovolts. So now I can work out my current is a lot larger, 2 amps. Put that in the I squared R formula, and I get 2 squared times the same resistance. This time I get, instead of my 62 watts, 4,800 watts. Significantly bigger. And it's because of that squared value, right? So you get a larger loss when you've got a higher current, when you've got a small voltage. So what you want to do is you want to step that voltage up as much as possible to decrease the current. So what we've looked at in this video is transmission lines, very basic introduction to transmission lines, and the fact that why do we step up the voltage? But the aim's really to step down the current. And the reason we do that is that we do lose some energy to heat. We can treat our transmission lines as a resistor, and that energy lost is equal to I squared R. If we decrease the current as much as possible, that decreases the power significantly, and that limits our loss of energy to heat.